Okay, it's 6 o'clock. Welcome, everyone. We're beginning again. So for everyone out there on the internet, what we're doing here is a UQ MATH7502 practical session on the statistics of data science or introductory maths related to data science, but it's pretty much mostly linear algebra that we're doing. And tonight in particular, we're going to look at some things related to QR decomposition and some other matrix problems. Okay? All right, so, well, I was about to introduce Walla, but she's having a chat. And so I'll just wait a moment. How are you going, Walla? Okay, so Walla's here. She's walking up to the stand, and she's about to do a couple of problems. And I will do two other problems after that. So the first half will be Walla presenting, and then I'll come back and have a chat with you about a couple of other problems. Okay, so see you soon. And here we have Walla.
Hi, everybody. Let's start with the question 1. In question 1, they ask, suppose that A1, A2, up to AK are orthonormal in vectors. That means the length of each one is n. A1 is a vector, A2 is a vector up to AK. And B1, B2, up to BK are scalars. These may be any number. Assume that X equal the summation of from I equal 1 to K for BI multiplied with AI. Express the norm of X in terms of B, which equal B1, B2 up to BK. Let's start to find the solution, and we need to express the norm of X in terms of B. Here they give you that X equal the summation of I equal 1 up to K. So X equal here the summation of I equal 1 up to K with BI AI. Let's try to expand the value of X. The value of X here, X equal B1 times A1 plus B2 times A2 up to BK times AK. So this is the value of X. They ask you to find the norm of X. We need to find the norm of X. Let's take the norm for both sides. We need to find the norm of X. The norm of X equal the norm of B1 A1 plus B2 A2 up to BK AK. This is the norm of X. And we know that the norm of X to power 2 equal X transpose times X. So let's try to find the norm of X squared and find the norm squared for both sides. So we need to find the norm of X squared, which equal to the norm of B1 A1 plus B2 A2 up to BK AK, and this is to power 2. So here, the norm of X squared equal the norm of B1 A1 B2 A2 plus BK AK to power 2. Now we need to expand this norm by substitute the norm of X in general, the norm of any terms, the norm of X squared equal X transpose times X. So we need to substitute the norm of B1 A1 B2 A2 up to BK AK. So we can write it as B1 A1 plus B2 A2 up to BK AK transpose multiply with B1 A1 plus B2 A2 up to BK AK. Okay? Yeah. We know that if we have A plus B transpose, this is equal A transpose plus B transpose. So here we have B1 A1 and here we have transpose. So we can write it as B1 times A1 transpose plus B2 times A2 transpose plus BK times AK transpose. All of this multiply with B1 A1 plus B2 A2 up to BK AK. Okay. Now we need to expand. We need to multiply each term from here, B1, A1 transpose, by each term in the second bracket. So we need to multiply B1, A1 transpose with B1, A1. We need to multiply B1, A1 transpose by B1, A2. We need to multiply B1, A1 transpose by BK, AK. So this is equal B1 times B1, this is will give us B1 squared, multiply with A1 transpose times A1. So this is equal B1 squared, multiply with A1 transpose times A1, plus we need to multiply B1 times B2 times A1 transpose times A2. So here we have B1 times B2 times A1 transpose times A2 plus up to B1 times BK multiply with A1 transpose times AK plus here we have B1 times BK times A1 transpose plus, AK. This is for the first term. Now we need to multiply B2 A2 transpose by the second bracket. So we need to multiply B2 A2 transpose by B1 A1. So plus B1 times B2 multiply with A2 transpose times A1 plus B2 times B2 from here we will get B2 to power 2 plus B2 to power 2 times A2 transpose times A2 plus B2 times BK multiply with A2 transpose times AK. B2 times BK multiply with A2 transpose times AK. Let's move to the last term plus, we can continue, plus BK multiply with AK transpose times B1 A1. So here plus B1 BK times AK transpose A1 plus BK AK transpose times B2 A2 plus B K AK transpose times B2 A2 plus the rest term BK times BK will give you BK to power 2 multiply with AK transpose times AK plus here we have BK times BK times AK transpose times AK. They give you at the beginning that A1, A2, O3 up to AN, all of these are orthonormal. And we know if they are orthonormal, it's equal to 0 when I equal J. If we have two vectors, if we have AI transpose times AJ, this is equal 0 when I not equal to J, and it's equal 1 when I equal to J. So in general, if we have two vectors to be orthonormal, it's equal 0 when I not equal to J, and it's equal 1 when I equal J. Let's look back here. We have A1 transpose times A1. When we multiply A1 transpose times A1, this will give us 1. So this term will give you B1 to power 2. Look here. Here we have A1 transpose times A2. I and J are not the same, so this element will be 0. Here we have B1 times BK multiply with A1 transpose times AK. Because here we have I and J not the same, so this is also will be a 0. Look here we have B1 times B2 multiplied with A2 transpose times A1. I and J are not the same, so this is also will be a 0. But here we have A2 transpose times A2. And here we have I and J are the same. This is will give 1. So this term will give you B2 to power 2. And here we have BK times BK multiplied with AK transpose times AK. Here we have K and here we have K. So this is will give us 1. And this term will be BK to power 2. So we can write it as so the norm of x to power 2 equal B1 squared plus B2 squared plus B3 squared up to BK squared. Okay, and we know that the norm in general, the norm of B squared equal the sum of Bj from j equal 1 up to k. So instead of B1 squared plus B2 squared up to BK squared, we can write the norm of B squared. So here we can write it as the norm of x squared equal the norm of B squared. So we can simplify the norm of x equal the norm of B. So we can write the norm of x by using B. And B here is a scalar, can be any number. So the norm of x equal the norm of B. And B here is a scalar. Is there any question about question 1? Okay. Let's move to question 2. And in question 2, they ask, consider the list of n vectors, A1, A2, up to AN, with AK equal the sum of I equal 1 up to K for EI, whereas K equal 1, 2 up to N. Describe what happens when we run the Gram-Schmidt algorithm on this list of vectors. We need to find the Q1, Q2 up to Qn. So the question asks you, find the value of the Q1, Q2 up to Qn. To solve this question, at the beginning, we need to know what's the vectors. Here we have, they give you the general formula. AK equals summation from I equal 1 up to K for EI. So what's the value of A1? The value of A1 equal E1. The value of A2 equal A1, E1 plus E2, E1 plus E2. And the value of A3 equal A1 plus E2 plus E3 and so on. We know that the value of E1, which is the unit vector, E1, the first term is 1 and the rest is 0. This is the vector E1. And the vector E2 equal, the first term is 0, the second term is 1 and the rest is 0. This is the second vector, which is E2. The third vector, for example, E3 here, we have 0, first row, second row is 0, and here we have 1. We have 1 in the third row, and the rest is 0. And you can see from here that E1, E2, E3 are the unit vector. That means the length of each one equal 1, or the norm equal 1. If you try to find the norm of E1 or the norm of E2 or the norm of En, just will be 1. Now from here, what's the value of A1? The value of A1 equal E1, which is 1, 0, and the rest is 0. What's the value of A2? The value of A2 equal E1 plus E2, which equal 1, 1, 0, 0, and the rest is 0. Just we need to add E1 plus E2. Here we have 1 plus 0, which is 1, 0 plus 1, which is 1, 0 plus 0 is 0. And AN equal, if you have AN, we need to add E1, E2 up to EN. It will be 1, 1, 1 up to N. All of these are 1. Now we need to apply Gram-Smith. Just to remember Gram-Smith, Gram-Smith said, given n vectors v1, v2 up to vk for I equal 1 to up to k. To find the qi tilde equal vi minus q1 transpose inner product with vi. All of these multiply with the q1 minus qi minus 1 transpose times vi, and all of these multiply with the qi minus 1. Let's try to find the value of q1 tilde. Now we need to find the value of q1 tilde. The value of q1 tilde after we apply Gram-Smith, q1 tilde equal v1. And in our case, we have ak equal summation of ei. We have ak equal summation from I equal 1 up to k for ei. So here, this is equal, when k equal 1, this will give you the first vector, v1. This is equal a1, which equal here, in this case, e1. Why? Because here we have, they give you that ak equal summation from I equal 1 up to k for ei. So q1 tilde equal e1. And we know from Gram-Smith, when q1 tilde not equal to 0, so that means that q1 tilde and the vectors are not linearly independent. When it's equal 0, we can say that they are linearly dependent and we can quit the algorithm. But now it's not equal to 0. So we need to continue. We need to find the value of q1. To find the value of q1, it's equal the value of q1 tilde divided by the norm of q1 tilde. This is equal q1 tilde divided by the norm of q1 tilde. So this is equal e1 divided by the norm of e1. And we know that e1 is the vector which all entries are 0 except just we have 1 in this vectors, and the length or the norm of this vector equal 1. So here we have e1 divided by 1, which equal e1. So we can find that q1 equal e1. This is the first thing. Now we can find that q1 equal e1. Let's try to find the value of q2, and we need to apply Gram-Smith again. The value of q2 by Gram-Smith equal v1 minus q1 transpose times v2. All of these multiply with q1. Let's try to substitute here in our question. Here we have, this is v2 minus q1 transpose times v2. Here there is an inner product, and all of these multiply with q1. Here v2 is the same as a2 minus q1 transpose. The value of the q1 transpose is e1 transpose. Here it's e1 transpose. Multiply with v2, and here v2 is a2, and all of these multiply with e1. Now we need to expand to see what the q2 will be. Let's try to write it using a number. A2 in general equal 1, 1, and the rest is 0. Minus, we need to multiply E1 transpose, which equal 1, 0, and the rest is 0 transpose, times A2, which equal 1, which equal 1, 1, and the rest is 0 times E1, which equal 1, 0, and the rest is 0. At the beginning, let's try to find the multiplication between E1 transpose times A2. 1 times 1 will be 1 plus 0 times 1 is 0, and the rest is 0. So when we multiply E1 transpose times E2, will give you just 1. So here we have 1, 1, 0, and the rest is 0, minus this multiplication will be just 1 minus this one multiply with E1, which is 1, 0, and the rest is 0. If we try to subtract, here 1 minus 1 is 0, 1 minus 0 is 1, and the rest is 0. And we defined the vector E2. The vector E2 is the first row is 0, and the second row is 1, and the rest is 0. It's similar like what we get here in Q2 tilde, which is 0, 1, and the rest is 0. So we can put this is equal E2. So Q2 tilde equal E2. Because it's not equal to 0, so we cannot say they are linearly dependent. We need to continue. We need to find the value of the Q2, the same thing. Q2 equal Q2 tilde divided by the norm of Q, the norm of the Q2. This is equal E2 divided by 1, the same thing, because E2 just have 1, and the rest, all of it are 0. So the value of the Q2 also here equal E2. This is the second thing. So we can find that Q1 equal E1, Q2 equal E2. Let's try to find Q3 to be sure about our result. Okay. Let's try to find the value of Q3. We need to apply Gram-Smith again. The value of Q3 will be V3, here we have A3 minus V3, here we have A3 multiply with Q1, which is here we have E1 times E1, which is the value of Q1, minus A3 times Q2, which is here A2, and all of these multiply with E2. If you try to expand and find the value of E3 times E1, it will be 1. This is will give you 1. And E3 times E2, and this is also will give you 1. So the value of Q3 tilde equal E3 minus E1 minus E2. The same thing, we need to find the value of Q3 tilde. We know that the value of Q3 is 1, 1, 1, and the rest is 0. Just we have 3 ones at the beginning. Minus E1, which is 1, 0, and the rest is 0. Minus E2, which is 0, 1, and the rest is 0. If you try to subtract 1 minus 0, this is will be 0. 1 minus 0 minus 1, this is also will be 0. 1 minus 0 minus 0, this is 1, and the rest is 0. This is the same as E3. And if you try to find the value of Q3, this is equal Q3 tilde divided by the norm of Q3 tilde. So this is equal E3 divided by, this is E3, the same thing like E2 and like E1, just have 1 in the interest and the rest is 0. So it's E3 divided by 1, which is equal E3. We can summarize that Q1 equal E1, Q2 equal E2, Q3 equal E3, and Qn equal En. This is the general formula for Q1, Q2, Q3, up to Qn if you try to find the Gram-Smith, okay, by using EIs. This is the first part in the question. Okay. Okay. In the second part, they ask you, is A1, A2 up to AN a basis in Rn? They ask you if A1, A2 up to AN make a basis or not. Yes, it's make a basis. Why? Because we can find that when we try to calculate Gram-Smith, it's not terminate. It will not be quit, because when we try to find the value of the Qn will be En, and it will not be 0. So E1, A1, A2 up to An is a basis, and the vectors are linearly independent. So we can say yes, because A1, A2 up to An are linearly independent, because Gram-Smith will not quit or terminate. So yes, they can make a basis. Okay, it's clear for you? Is there any question about the question 1 and the question 2? And now you can continue with Sam to solve the question 3 and the question 4.
Okay, it looks like I've got a bit of extra time. All righty, last session we had a little bit of technical difficulties, which made the time a little less, but this time we don't. So I'll just get organized and then I'll continue with the next questions. Okay, so here we go. Question 3, let A and B be two M by N matrices. Determine whether A equals B always or sometimes. Explain and prove. All right, so in these two cases, so I'll just have a look at these with you. Now the first case is for all X in Rn, so that's vectors with length n having real entries. We have AX equals BX. So the question is, do we always then have A equal to B in this question? Now the second one asks, if this holds only for some X in Rn, that AX equals B, do we have A equal to B always or only sometimes? Okay, now let's have a look first at the first one. So given that we can assume that X is any because it holds for all vectors in Rn, so that allows us to choose, okay? So we can choose, since we know that it happens for E1, we can say we know A E1 is equal to B E1. Okay, now let's have a look at the left-hand side of this. What is that product on the left-hand side? So AE1, now remember, this is the same E1 that Walla introduced earlier. It has the top entry equal to 1 and the entries below it equal to 0. So if we take the product of A with that vector, what we have is the top left entry times 1 and then plus several zeros, right? And so what we end up with is the top left entry of A. Okay, carrying on, now we do this with the second row of A, but we have A21 times 1 gives A21, right? Because the rest are zeros. And so what we get from this is that we just have the first, or the leftmost column of the matrix A as the result of the left-hand side here. Okay, now likewise, we have, for this matrix, B times E1, we also have the leftmost column of the matrix B as the result. And so what this says is that columns 1 are equal. Okay? Right, now, remember that says for all, so we can go and say, well, let's let x be, in this case, E2. Okay, so we also have a E2 is equal to B E2. And so again, for the same reasons, because E2 is 0, 1, 0, dot, 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 0, where all the entries below the 1 are equal to 0. So when we multiply this left-hand side out, what we have is the entry in the second column, so A subscript 1, 2 times 1, and then the rest are zeros that we're adding to that, so we just get A21. Likewise, in the next row, we have A22 times 1 plus several zeros, right? And so we end up with the second column of A. Likewise, here we end up with the second column of B. So this says columns 2 are equal. Right? Okay, good. Now, of course, you can take EJ. So we also have A times E subscript J is equal to B E subscript J, because again, this happens for all X in Rn. Okay, so this, when we multiply those out, what we have then is that columns J are equal. Okay, so now let's summarize all of that. We have every column of A is equal to every corresponding column of B, right? So the first column of A is equal to the first column of B, the second column of A is equal to the second column of B, and so on, all the way up to N. So the only possible conclusion is, since every column are equal, that A has to be equal to B, right? So hence, the matrix A, the entire matrix A is equal to the entire matrix B. Okay, great, that's easy. Now, next one. Okay, so the next one says for some X belonging to Rn, we have AX is equal to BX. But here we're not assuming that it's all X in Rn, for which this happens, right? Okay, so what we want to think about here is we want to rearrange this equation to get some insight. Okay, so here we have AX minus BX is equal to the 0 vector, but I'm going to write that by factorizing this. So write this A minus B times X is equal to the 0 vector. Okay, because now we see that X should belong to the null space of A. All right, so in other words, our question is the null space of A minus B, is it trivial? Or is there something in it that's not the 0 vector? All right, so let's just see if we can find a matrix that has, and in fact, we can even choose a 2 by 2 matrix, right? To illustrate the point. So let's choose a 2 by 2 matrix that has a non-trivial null space. Okay, so let's let C be equal to minus 2, 2, and then 3 minus 3. Okay, and now look at the null space of this. So if we row reduce this, well, then we have minus, well, this is not completely row reduced, okay? So what I'm doing is subtracting a multiple of the second row from the first, and I'll put zeros down there. And then here I'll just put minus 1, 1. Okay, so it's not totally row reduced. So in the first row, I've just divided throughout by 2. Okay, so these are, yeah, they have the same row space. Okay, so here we've got such a matrix. Now, can we find an element that's in the null space, a simple element? Well, yes, we can, because minus 1, 1, 0, 0 times 1, 1 is equal to 0, 0, okay, which is the 0 vector. So we found that 1, 1 belongs to the null space of C. Okay, now that we've got that, can we find two distinct matrices A and B that have a difference that's equal to C? Well, yes, we can, right? So let's let A be equal to 1, 0, 2 minus 1, and B be equal to 3 minus 2 minus 1, 2, okay? Now we take the difference, A minus B. So A minus B is equal to 1 minus 3 is minus 2, 0 minus minus 2 is 2, 2 minus minus 1 is 3, and minus 1 minus 2 is minus 3. So we actually have C as the difference of A minus B, okay? And we already know that 1, 1 is a member of the null space of C. Okay, so what does this mean? Well, what we found is that since we know that A 1, 1 is equal to B 1, 1, because 1, 1 is in the null space of A minus B, right? And so you just rearrange this equation. You have A minus B times 1, 1 gives you the 0 vector. So this therefore holds. Okay, so we have an example of this right here, right? For some x, where x in this case is 1, 1, right? But here you see that A is not equal to B. So, but A is not equal to B. Okay, so the answer to this question is no, not always do we have A equal to B. In this case, we only have this true sometimes. Okay, do you have any questions about that one? Incidentally, we'll probably end up finishing a little bit early. So if we do, I'll just leave that time for asking any last questions about your assignment before that's due to be handed in. Okay, moving on. Right, next question, next and last question of this problem set says, suppose we have an n by k matrix A, and we have a QR decomposition for it. Okay, Q times R, where this is applying the Gram-Schmidt process to the matrix A and obtaining a QR decomposition of that matrix, okay? So given that we know that, then we also know that R is upper triangular, right? So meaning it has zeros below the main diagonal, and we know that Q is orthogonal and the product is A, right? So that's what we know. All right, so now let's define, put A subscript T to mean simply the first T columns of the matrix A right there. Okay, so that then is an n by T matrix. And then we will let Q subscript T be the first T columns of the orthogonal matrix Q. So that's an n by T matrix. And so we'll define this for every T. So for T equals 1, 2, all the way up to K. Okay, similarly, but slightly different, we'll put R subscript T to be the first T columns, but truncated. The first T columns of R, but truncated so that they have length T, all right? So they're possibly somewhat shorter in length in these column vectors than the original matrix T. And this will be a T by T. So this one is square, all right? And I'll give you a visual of this soon so that you can fully digest all of these definitions. Okay, so we're asked here to prove that AT defined to be QT times RT is in fact the QR decomposition of AT. Okay, so in other words, would the Gram-Schmidt process applied to AT give you an orthogonal matrix QT times an upper triangular matrix RT? okay? And so where those are defined as above by pulling out the first T columns and so on. Okay, so given that we've got that, so let's begin. Now, I'll inevitably get tired of drawing. There's a lot of tedious things for me to draw. So eventually, I'll probably just show you what I've already got written down, okay? So I will begin by basically writing a sort of a diagram of the product of Q and R, okay? And then I'll say I want to restrict attention to QT, RT within that. Okay, so I will say first, well, let's just write out what Q would be. So I'll leave lots of space for this. Okay, so here's my Q, here's my R. But then I'm going to restrict attention, as I said earlier, to a two by two matrix in R. That would be R subscript 2, and an n by 2 matrix Q2, right? Okay, so I'll just draw boxes around those parts. Right, so here we go, Q11, and then we have Q12, and then we have a dot, 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 and then we have Q1n. Okay, so that's our first row, and then we go Q21, Q22, dot, 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 Q2n. All right, then we have vertical dots, and here we have Qn1 and Qn2, and then over here we have Qnn. Okay, and then dots, and then dots, and then we'll put a diagonal dots there. Okay, so this here is Q. All of this here is Q, right? But I want to just draw a line here and say I'm going to think about this part of Q, all right? And basically scratch the rest of it out because that's the whole other part of Q. All right, so this part of it here, this is Q2, this part, right? And the whole thing is Q. All right, now let's do the same with R. So we have R11, we have R12, R13, dot, 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 R1K. Okay, and then below that, remember this is upper triangular, so now we have a 0 below that diagonal entry. And then here we have R22, R23, and so on, dot, 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 R2K. Okay, great, that's the second row. Now we have zeros below this 0 in the first column of R, and of course it ends with 0. And then another dot, dot, dot. The entry just below that R2 is 0, and then we end with 0. Okay, and so over here we have a vertical dot, dot, dot as well. And we have an R subscript NK. All right, now we've got a 0 just to the left of that, but we'll go ahead and put a dot, dot, dot. And then we need a diagonal dot, dot, dot. Okay, so this is all of R, right? But now I'm going to draw a box around just the part we're going to focus on here, which is R2. And I need a place to point to it. Okay, I'll just point to it here, R2, and then I'll just send a curly little arrow through there. This is R2, right? Now the whole thing is R. This is R, all of it, all of that. Okay, so if we took the whole product, this would be A, right? But since I'm only referring to the parts that I put a box around, the boxed parts, that's QT, RT, where T is 2, okay? And since I'm doing some kind of, I guess, loose talking, because I've drawn a diagram, right? And so this is not exactly perfect mathematics here. So let's just put a box around this as well, right? Just because we're doing some funny kind of writing. Okay, all right, but I hope it's descriptive. Okay, so now let's just calculate what Q2 R2 is. Right, so if we multiplied this here, what we would have is we take these two entries right here, we'd rotate that and multiply it by the two entries in this column, first column right here. But we've got a 0 there, so it's actually the result gives us just Q11, R11, correct? Okay, and now next we take these two entries and multiply by these two. But this time we have a sum, don't we? Okay, so the next one, we have Q11, R11 plus Q12, R22, but we can express this as a sum, even though it's a short sum. Let's sum over S. So S goes from 1 to 2, and we have Q1S, R, S2. Now notice that the 1 and the 2 here on the outsides, they correspond to the 1, 2 entry of Q2, R2, okay? Right, and then that ends that matrix there because it only has 2 columns, but we have more coming down here, right? So next we take this and we multiply it by this first column, all right? But we end up with Q21, R11, right? Okay, and here we have a sum. What we have in it is Q2SRS2, and the 2, 2 there is the 2, 2 entry of this matrix, but we're summing from S equals 1 to 2. Okay, and then there's a dot, dot, dot. This pattern continues, and down the bottom we have Qn1 and R11, and then here we have a sum from S equals 1 to 2, QNSRS2. Okay, so we've done that product, Q2 times R2. Okay, great. So now we'll claim that this is actually the same as the first 2 columns of A, right? And so let's have a look at what would happen if we actually multiplied out the entire Q times the entire R, right? So let's do this. If we take this entire top row by taking all of Q times all of the first column of R, right? Because of all those zeros down there, we still end up with Q11, R11, right? And so we actually have the same thing as that. Okay, now we continue on. We go the second row times, so if I'm doing it this way, I'm talking about the entry below it, right? Okay, so second row times this first column gives us the entry below. And again, because of all these zeros, we have Q21, R11. And so that's the same as this, right? And so on. So we have the same entries here in this first column when we multiply the whole thing. All right, now continuing, if we do this by adding another column here, okay, so all of Q times all of R, so we take the first row, multiply by the second column, and that's the 1, 2 entry. All right, but here we have Q11 by R12 plus Q12 by R22, and then all these zeros here mean all of the rest of those don't matter in the sum, right? Because they're zero, adding 0. Okay, so we still only have a sum of 2 things. So in other words, it's exactly the same as this, and so on. All of these times that down this column give us the very same things. Okay, so I'll just note here the same result as first 2 columns of all of A, which of course is QR, and that's because of zeros below the main diagonal. Okay? All right, so we're basically, hopefully, almost convinced now. So I think my hand is getting tired, so I'm just going to flash up the next page that I've already written. Okay, so where I actually multiply out all of Q times all of R, right? And so that's here. Now, so far we've just looked at the first two columns of all of Q times all of R, right? And so this is that part. This is that part right here. Okay, so now you notice that we stopped at 2 here, right? But we could say that that's the same thing as if we went to n, right? And so this would be, if I had an n there rather than a 2, that would be the usual definition for the product of two matrices, right? Where the outside terms, they are the entry, that's the 1, 2 entry of this product, and so on, right? But it's just the fact that there are zeros below the main diagonal that I can state that this stops at the same place as that j does, the 2, right? And carrying on, this entry here of all of Q times all of R, it's just the sum of 3 things this time, right? Because of the zeros below the main diagonal. So I have Q1S S times RS3, and I'm summing as S goes from 1 to 3, but I can stop at 3 here because of the zeros below the main diagonal, all right? And so on. So here we see a fancy pattern in all of this, which you can summarize in this way, right? So the Aij entry of A, which is the product of Q and R, is a sum as S goes from 1 up to J of QIS times RSJ. And this is an n by k matrix, right? Okay, so now if we just look at QT times RT, which remember was the first T columns of Q times that square T by T submatrix of R, right? So this we found has the very same definition, except it's an n by T matrix, right? And so that's just saying that this is the first T columns of this matrix A, right? And so the final thing we need to observe is that that this QT here, it also has orthogonal columns in it, right? Because it's a submatrix of Q, right? And also the sub matrix of R, that is R subscript T, that is upper triangular as well, right? And so we have a QR decomposition, right? And it's going to get the same result as if you applied the Gram-Schmidt process on A2 there, and so on and so on. Because in each case, we're just adding another column, all right? So I hope that sort of gives you a visual description of what's going on here. That can help you think about the problem. Okay, great. So that's all I have to say about this problem set, unless you have any questions at this point. All good? Okay. How you going, Jonathan?
Yeah. Maybe a flash later.
A flash?
Yeah.
A flash of what?
How to change the matrix of question 4.
How to change the matrices in question 4? You mean what I just...
Yeah, you just use your hand to make a great flash vision, like a flash vision, like shows.
Okay, right. All right, so look, I think next we should have a look at your assignment, and I'll just give you a last opportunity to ask any questions about it. So I'm going to pull up your assignment. And if you have any questions, I guess now's the time. So it'll take me a moment to find this.
Hey, Sam,
And it looks like actually, I mean, I didn't expect to take this long, but it's 6:54, so we're just about out of time. If you need to go, that's okay. So here's the assignment, and it looks like it's due. Is that today? It's today.
Yes. Yeah.
Oh, okay. So you're probably already done with it. So I guess you don't have any questions about this, because presumably you've already submitted it, right? So I got a little thrown off because someone in the last session had a question And so
Hey, Sam,
I didn't
can you
quite
hear me, Sam?
realize what the date was. Today's the 10th. Okay. So any questions about this?
Hey, Sam.
I guess not then. Okay, well, let's knock off for the night. So thanks everyone for
Hey,
participating.
Sam, can you hear me?
And I'll see you next week if you're here. All
Hey,
right.
Sam.
Good night.
Sam.
The assignment question one's number can be simple.
You hope next time question 1 is simple?
The number maybe simple.
Of the number, like you mean less than 8?
No, question one. Question one. It's a two keep.
Oh, you mean it has many parts?
Yeah.
Oh, yeah.
No, not many parts. It's hard to calculate because
I
the
see.
number.
The numbers are not integers. Well, did you remember how I did my example? In my example, and it's on YouTube, of course, but
Yes.
I did it by totally avoiding fractions until the last minute, right? And so I think that's always a good idea if you're going to do it by hand. Avoid fractions until the last possible moment, because once you get fractions in there, they're everywhere, right? And so I don't know why, but humans seem to struggle with fractions. Okay, sure. All right, guys, see you later. Thank you. Oh, hang on, Jonathan's got a question. I think your audio might be turned down. Okay, sorry about that. I was probably just a little too far away from the microphone, Jonathan. So
Can you hear me now?
we'll try to work on that next time.
Can you
Thanks
hear
for
me?
pointing it out.
Sam, can you hear me? Sam, can you hear me?
Oh, right. I think maybe what you're saying, Jonathan, is that our speakers are turned off. That's possibly the case. Yeah, so no, I can't hear you, so we'll have to do that next time. But did you have any questions you want to put in the chat? Because I doubt that I'll be able to quickly work out the volume here. Okay. Hang on, is this a volume button? I don't know. Okay, so you just had a question about the Jupyter Notebook. Yep. Okay, so you finished your assignment and went to print it and all looked good. ... That sounds ominous. And the formatting when printing is way off. Like, what do you mean way off? So you didn't get the symbols you were hoping for? Is that the case, or? Certain sections are garbled. Okay, so, right, and that's a physical paper submission, is it? So if that's the case, then I wonder if you could simply take a screenshot if it's not too much work, because I mean, if you've still got the file and you took a screenshot and then printed the screenshot, that may be better. It's just a thought, okay? That is if it's totally unreadable. Yeah, anyway. So I hope it works out for you there. And I mean, I'm not the final word on the timing of submission, but I would think that if it takes you a little bit of extra time just to take a screenshot and get a visible format, then that's probably okay. But of course, I mean, Yoni has the final say on late submissions and whether or not that's okay, right? So don't take my word on that. But I'm just speculating that's probably okay. Okay, Yoni said midnight. Okay, so I think we're good, yeah. So if you're not in Australia, then you have, what is it, 7 + 5 = 12. Okay, so that gives you 5 hours. All right, thanks, Jonathan. All right, good night, thanks, see you next week. Okay, so I'll end the session.